Today we're going to learn how to find the distance between 2 points using the distance formula. And to understand the distance formula, there are 2 things you need to know. One is the Pythagorean theorem, and the other is how to find the distance between 2 numbers on the real number line. If you understand the Pythagorean theorem and how to find the distance between points on the number line, you'll have no problem understanding the distance formula. But let's do a quick review. The Pythagorean theorem says that if you have a right triangle, that is a triangle with a 90-degree angle, and let's say the lengths of the 3 sides are A, B, and C, then the lengths of these 3 sides are all related, and the relationship is A squared plus B squared equals C squared. This formula only works for right triangles. It does not work for acute triangles or obtuse triangles. Next, let's remind ourselves how to find the distance between points on a real number line. Suppose we have 2 numbers, and let's call them R and S. And what we want to do is find the distance between these 2 numbers. Now, if you know that S is bigger than R, then the distance is just S minus R. But oftentimes in algebra, you'll be working with variables, in which case you won't know if one number is bigger than the other. So in that case, what you want to do is take the absolute value of the difference between the 2 numbers. By taking the absolute value, you're going to guarantee that you get a positive number. Now that we've reminded ourselves of these 2 results, let's dive in and learn how to find the distance between points. For our first example, we're going to find the distance between the point 2, 1, which is right here, and the point 8, 9, which is right here. Now what we want to do is find the distance between these 2 points, and I'm going to call the distance D for now. We'll find out what it is in a moment. The trick is to turn this into a right triangle. So here we have a right triangle, and this is where we're going to use the 2 things we talked about in the opening. We're going to use the Pythagorean theorem to find the length of D once we know the length of the 2 sides. And to find the lengths of the 2 sides, what we're going to do is use that formula for finding the distance between 2 numbers on the real number line. Okay, so let's do that now. Let's look at this bottom leg of the triangle. If you were to kind of project it down to the x-axis, it starts at the point 2 and goes all the way over to 8. And I got that because I'm looking at the x-coordinates of the 2 points. The left point has an x-coordinate of 2, and the top point has an x-coordinate of 8. So that means the length of this leg is the same thing as the distance between 8 and 2 on the x-axis. So using the formula that we talked about in the opening, the distance between 8 and 2 is just the absolute value of 8 minus 2, which is equal to 6. So the length of this leg of the triangle is 6. And now to find the length of the other leg of the triangle, imagine projecting these 2 points onto the y-axis. In that case, the bottom point starts here because it has a y-coordinate of 1, and that is 1 on the y-axis, and the top point has a y-coordinate of 9. So the distance between 1 and 9 on the y-axis is the same thing as the length of the other leg of the triangle. And once again, we use the formula we saw in the beginning, and that is the absolute value of 9 minus 1 is 8. So the length of this leg of the triangle is 8. So now to find D, we use the Pythagorean theorem, and I'll do that over here on the right. So 6 squared plus 8 squared equals D squared. Multiplying out, we get 36 plus 64 equals D squared, or 100 equals D squared. Let me just flip it around so the variable's on the left here. So now to find D, we just take the square root of both sides, and that gives us D is plus or minus the square root of 100, or plus or minus 10. Now because we're talking about distances, distances are positive, so the distance between these 2 points is 10. Let's see another example. For this example, let's find the distance between the point -1, 3, which is right here, and the point 2, -1. Let me draw the line segment connecting these 2 points. There we go. Like before, what we're going to do is we're going to create a right triangle having this line segment as its hypotenuse. We're going to call the distance between these 2 points d. And like before, what we want to do is now find the lengths of the 2 legs. Now, the length of this bottom leg here is the same thing as this distance on the x-axis. And that is the distance between -1 on the x-axis and 2 on the x-axis. I'm just using the x-coordinates of the 2 points. So to find the length of that leg, we use the absolute value of 2 minus -1, which is 3. So the length of this bottom leg of the triangle is 3. Now let's find the length of this second leg of the triangle. The length of this leg is the length of this part of the y-axis, which is just the difference between the y-coordinates of the 2 points. This coordinate up here is 3, and this coordinate down here is -1. So to find the distance between those, we take the absolute value of 3 minus -1, which is 4. So to make this a little cleaner, what I'm going to do is draw up here what we now have. If you were to take away the x and y axes, and all the numbers and scribbling I've done over there, we have a triangle, a right triangle, where the length of one leg is 3 and the other leg is 4. The distance between these 2 points is the length of this hypotenuse. We use the Pythagorean theorem, which says that 3 squared plus 4 squared equals d squared, or 9 plus 16 equals d squared, or adding and flipping around, we get d squared equals 25. Like before, to solve this, we take the square root of both sides. That gives us the square root of d squared equals plus or minus the square root of 25, or d equals plus or minus 5. Now these are the 2 number solutions to the equation, but the solution to the problem is the distance. And like the previous example, distances are always positive numbers. So the distance between these 2 points is 5. Let's see one more example, and I'm going to be a little tidier with what I write so that you can practice using your imagination and memory to kind of follow along with what I do. For this example, we're going to be working in the 3rd quadrant. So here are our axes, and I'll do my best to keep the diagram a lot simpler than the previous 2. The first point we'll be looking at is -8, -1. And the second point is -2, -5, which is, let's say, right around there. And once again, we want to find the distance between these 2, which we will call d. Like before, we're going to make a right triangle, but to mix things up a bit, we're going to have an upside down right triangle. But that's okay. The Pythagorean theorem works upside down, left and right, all different ways. To find the lengths of the 2 legs, what we're going to do is find this distance along the x-axis and find this distance along the y-axis, which once again is just looking at the distance between the x-coordinates and the distance between the y-coordinates. So this leg here on the x-axis, the length of that is the absolute value of -8 minus -2. Lots of negatives here. -8 minus -2 is -8 plus 2, -6, or 6. And for the segment along the y-axis, the length of that is the absolute value of -1 minus -5, which is equal to -1 plus 5, which is equal to 4. The length of this leg is 6, the length of this leg is 4, and what we're wanting to find is the length of the hypotenuse, d. Once again, using the Pythagorean theorem, we have d squared is equal to 4 squared plus 6 squared. So d squared equals 16 plus 36, which is equal to 52. So d equals plus or minus the square root of 52. And because we're working with distances which are positive, d is equal to the square root of 52. And if you're a fan of simplifying radicals, you can also write this as d equals 2 times the square root of 13. So now what I'm going to do is take the 3 examples that we just saw and use them to show you what the distance formula is and where it comes from. And to do this, we're going to work very abstractly. We have a plane, and let's say we have 2 points in this plane. This first one, we're not going to pick specific numbers, we're going to use variables instead. has x1 as the x-coordinate and y1 as the y-coordinate. I'm using ones here because this is the first point, point number 1. And let's say point number 2 is up here, and it has x2 as its x-coordinate and y2 as its y-coordinate. So, point 1 is x1, y1, and point 2 has coordinates x2, y2. The idea, and this is where the distance formula comes from, is you make this right triangle, and you want to find the distance d between them, and you first find the lengths of the two legs. And so we'll say leg 1, which we'll call this one, has length absolute value of x1 minus x2. Here's an example of, once again, where you want to use absolute value signs because we don't know the numbers x1, x2. We don't know what they are. We don't know which one is larger than the other. So the other leg of the triangle, which we will call leg 2, has length absolute value of y1 minus y2. So now, to find the length of d, we use the Pythagorean theorem, which says take the length of the first leg, absolute value of x1 minus x2 squared, plus the second leg squared, absolute value of y1 minus y2 squared, equals d squared. Now this is an interesting point. x1 minus x2, let me write that here. We don't know if that's positive or negative, but if you square it, you're guaranteed to get a positive number. So with that in mind, you can kind of drop the absolute value signs, because by squaring it, if there is a negative sign, it's going away. And once again, if we square the difference between the y-coordinates, we can drop the absolute value there as well. Now, like before, we take the square root of both sides, and we always take the positive one because we're looking at lengths. That gives us the square root of x1 minus x2 squared plus y1 minus y2 squared. This is the distance formula. Oftentimes you'll see this and people will ask you to memorize it, but you don't really have to memorize it when you think about this is nothing more than the Pythagorean theorem, except working with coordinates. But if you want, you can go ahead and memorize it too. It's now time to level up. We're going to take what we just learned and go to a higher dimension. So here we have our x-axis, our y-axis, and our z-axis. So we're now in the wonderful world of 3D space. Suppose we have 2 points in space. Now, points in the plane have an x and y coordinate. Points in space have an x, y, and z coordinate. So let's say we have a point here, which we'll call P, and it has coordinates x1, y1, z1. And we pick a second point somewhere else in space, which we will call Q, and it has coordinates x2, y2, z2. Now here, if we were to connect these 2 points, in 3D space, you can make a right triangle again. And we want to find the distance between them. So what you would first need to do is find the length of this leg, and then you would need to find the length of this leg. Now, when you go through and do this, I'm not going to do the calculations here and derive this one, but if you want, you can dive in and do this yourself. What you will find is that the distance between these 2 points in 3D space turns out to be x1 minus x2 squared plus y1 minus y2 squared. Same thing as the 2D distance formula so far, but then there's also z1 minus z2 squared. So when you move up to 3 dimensions, there's a 3-dimensional distance formula. And the only difference between 2 and 3 dimensions is you now also want to include the difference between the z coordinates as well. And we're now going to move up to pro level. Imagine you live in hyperspace, more than 3 dimensions. In fact, we're going to say we're living in n dimensions, where n could be 4, it could be 40, it could be 1,000. But we're no longer living in a 3-dimensional space, which means we can no longer draw the points. But by analogy, we can say, let's say we have a point P. So how do we write the coordinates? Because it's possible that n is greater than 26, the number of letters. So we can't use different letters for each coordinate anymore. So what you do here in very high dimensional space is you now rely on using numbers to designate the coordinates. So we'll use the letter A to represent all of them, but it's the subscript, the little number here that lets you know is it the first coordinate, the second coordinate, the third coordinate, etc. So now we have a second point, Q, let's say, and for this we'll use the letter B. And if we want to find the distance between these 2 points, which you can also write as this, the letters P and Q with a line over it, that represents the length between P and Q, this is the distance, and the formula here is A1 minus B1 squared plus A2 minus B2 squared plus on and on and on until you get to the end with AN minus BN squared. So this is the n-dimensional distance formula. And when you start to move into more advanced geometry, oftentimes people will start to use a different word rather than distance. They'll often use the word metric. And a metric is just a function, it's just a way to calculate the distance between 2 points in some type of space that you're living in. But at the same time, you can also use distance, and mathematicians and physicists and everyone else will know what you're talking about. So this is the formula for finding the distance between 2 points anywhere in hyperspace.